Alright guys, so this first video is going to be a refresher of thermochemistry from Chem 1 with some of our calculations that we did. Starting off, we looked at how heat changes occur in physical processes. So this is whenever the temperature was changing, and then in a little bit we'll look at what happens whenever the phase changes. So in Chem 1 we had this equation, the Q equals mc delta T. Remember, Q is our change in heat. This is typically how much heat is absorbed or released, and it's typically measured in joules. You may also see it in calories, but then we would have other variables that take into account being in calories instead of joules. M is going to be our mass in grams. C is our specific heat, and remember this is unique for every substance. And water, there's a different specific heat depending on if it is solid, liquid, or gas. And the unit for specific heat is that joules per gram degree Celsius. And then the triangle T is delta T. That is going to be our change in temperature, and we can record that in Celsius as well. And remember, with our change in temperature, we typically do the final temperature, minus the initial temperature. That way we know if it was an increase in temperature or a decrease in temperature. So let's look at a problem with this. Here it says the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. What is the specific heat of copper? So using our equation, the Q equals mc delta T, plug in what variables we know. So it told us the mass is that 95.4 grams. We are looking for the specific heat, which is C. And then it told us copper's temperature increased from 25 degrees Celsius to 48 degrees Celsius. So we're going to do the 48 minus the 25. Now you could have also substituted that is 23. So you could have plugged that in as well. And then it tells us that is whenever the metal absorbs 849 joules. And remember, absorbing energy is going to be a positive Q value. So whenever we are trying to solve for C, we have to divide by the 95.4 and divide by that 23. And in terms of sig figs, pay attention to how many sig figs the non-constants have. So like our Q value here had 3. Our mass had 3, and our temperature also had 3, because whenever you subtract, it goes the least number of decimal places. So this would end up being 0.387, and the unit for specific heat, we did the joules divided by grams divided by the temperature change. So that's the joules divided by grams degrees Celsius. That was one of the basic chem calculations we had from Chem 1. Let's look at another one. Here it wants to know how much heat is required to raise the temperature of 250 grams of water by 52 degrees Celsius. So this one, we are going through a temperature change. It doesn't say anything about a phase change. And it also didn't tell us that it was like going over the melting point or over the boiling point. So we kind of assume that it's liquid water unless we're told otherwise. So for this, we're looking for heat. So we're solving for Q in this instance. Our M, our mass, is that 250 grams. C, specific heat for water. This would typically be given to you in a question, but liquid water specific heat is 4.18 joules per gram degree Celsius. And then it told us we raised the temperature 52 degrees Celsius. So that means they already subtracted it for us. so we don't have to worry about that part. Whenever we multiply these together, we get 54,340 joules. In terms of sig figs, here our temperature change only had 2 sig figs. So if we round this to 2 sig figs, it's 54,000 joules. You can also put this in kilojoules. So this would just be 54 kilojoules. So be careful with sig figs on these. They can be rather tricky, but pay attention to those as we go. What gets a little bit more complicated is whenever we also start looking at if we're changing phases or going through a melting point, boiling point, things like that. So a heating and cooling curve is something that we did have in Chem 1. Looking at the heating curve, it's a graph of the temperature versus time for a process where energy is added at a constant rate. So looking as energy is added to a system, does temperature increase? Does it go through a phase change? What's happening at different points in time? So this shows the physical changes that occur as heat is added. So whether there's a change in temperature and a change in state, or it could just be one or the other. So we pretty much look exclusively at the heating and cooling curve for water. Other ones may show up, but water is the one that we tend to focus on the most because we deal with a lot of substances with water. So looking at the heating and cooling curve, we said that it graphs the temperature compared to time. Sometimes you'll also see energy on this bottom one because we said it's time is going by as a constant amount of energy is being added. So sometimes you'll see time on the bottom, sometimes you'll see energy. Something to note with water, it is going to have this basic zigzag pattern, and it will have 3 slanted parts and then 2 flat lines. Those flat lines occur at the melting point and boiling point. So notice this bottom flat line for water is 0 degrees Celsius. That's the melting point for water. That top flat line is at 100. That is going to be the boiling point for water. The slanted lines represent our different states of matter that we have. So if it is colder than 0 degrees Celsius, it is going to end up being a solid. Between 0 and 100, water exists as a liquid. And then above 100, water is going to exist as gas or steam. You may see both terms. And then whenever it is on a flat line at the melting point or boiling point, that is whenever it was going through a phase change. So notice that bottom flat line at 0 degrees Celsius, it is melting. That top flat line at 100 degrees Celsius, it is vaporizing or boiling. When added heat changes the temperature, so these are going to be on those slanted parts of our graph, we are able to use that equation with specific heat. So the Q equals MC delta T. And remember, C specific heat is a constant for each substance in its state of matter. So for water, there is a different specific heat if it is a solid, liquid, and a gas. So here, note that whenever water is a solid, that constant for specific heat is 2.1. Whenever it is a liquid, that constant is 4.18. And whenever it is a gas, that constant is 1.99. So we said added heat changed the temperature. That happened on the slanted parts. But there were parts where heat was changing, but temperature did not. Those are going to be our phase changes, those changes in state. Those were the flat line parts of the curve. Whenever it is going through a phase change, temperature did not change. So we have to use this formula of Q equals M delta H. And in Chem 1, we typically used M as mass because our delta H values were in like joules per gram. One thing that you'll notice with our AP values is they will be in kilojoules per mole. So we will have to account for that whenever we do some of these practice problems. So in Chem 1, we did have those delta H values. Remember, melting, the amount of energy needed to melt 1 gram of a substance, which in our case will end up being 1 mole of a substance because of our units. Melting is going to be the heat of fusion. That vaporization or boiling is going to be heat of vaporization. So our values we're typically given in AP, notice that these are in kilojoules per mole. So whenever we do those problems with delta H, we will have to change from grams into moles. That way our units cancel out properly. That is going to be something extra that we did not have to do in Chem 1 because those constants were in joules per gram instead of kilojoules per mole. So let's look at a problem with the heating and cooling curve. And if you remember from Chem 1, since we have a different formula for the slanted parts and the phase changes, each segment of the curve is going to be a different problem. So if we're going from a solid up to a gas, we are going through all 5 line segments. So we will have 5 different problems for these. So let's look at one together. We want to know how much heat is required to convert 55 grams of liquid water at 22 degrees Celsius into steam at 105 degrees Celsius. And I'm going to draw a heating and cooling curve up in the corner so we can see kind of where we're starting and where we're stopping. This may help you figure out what steps you need to take. And remember, whenever we have those slanted parts, our temperature is changing, so we can use the Q equals MC delta T. Those flat lines, our phase is changing, but temperature is the same. So that's the Q equals M delta H. Sometimes you'll also see this written as N delta H, because remember, N represents moles. So you may see it both ways. But looking at this problem, it says we're converting from liquid water at 22 degrees Celsius. So remember, our flat lines are at 0 and 100. So 22 degrees Celsius is going to be here somewhere in the liquid stage. And we're going into steam at 105 degrees Celsius. That's going to be up here in the gas stage. So in order to connect those dots, we have to go through 3 different line segments. We have to go up the liquid line segment. We're going to have to change from a liquid into a gas. And then we're going to have to go up the gas line segment. So we are going to have 3 different steps to go through this process. So focus on one of them at a time. So whenever it is a liquid, let me change colors so you can see a little bit better. So whenever it is liquid, we have to go from the 22 degrees up to 100 where it reaches that flat line. The temperature is changing, so we can use that first equation, the Q equals MC delta T. We're solving for Q. M, our mass, is 55. C, the specific heat of liquid water, and this would typically be given within a problem or you would have a table to reference. But for liquid water, it's 4.18. And then our change in temperature. So the liquid water is only going up to 100. It doesn't go past that flat line. So our change in temperature is going to be the 100 minus the 22 degrees Celsius. And that, if we multiply across, is going to be 17,932.2 joules. sig fig wise, I'm going to come back in a moment and look at sig figs, and you'll see why. Whenever we have to do the liquid to gas stage, it's going across that flat line. So temperature is not changing. We have to use that Q equals N delta H formula. It gave us a mass of 55 grams, but we said because our unit for delta H is in kilojoules per mole, we have to change from grams into mole. So we have to divide by the molar mass of water to change into moles of water, and that's the 18.016. And that will change into moles, and then we can multiply by the delta H value. And this, because we're going from liquid to gas, it is the heat of vaporization value, which was the 40.7 kilojoules per mole. So this, and I'm going to tell you our mass had 3 sig figs. We'll leave this at 3 sig figs. This is going to be 124 kilojoules. Now we're not done, but we know at the end we're going to have to add these together. Our first problem ended in joules, but our second problem ended in kilojoules. So what you're going to want to do is anything that ends up being joules, you are going to want to change into kilojoules. That way your final answer when you add them together is also in kilojoules and our units match. So here's where I said I was going to come back and do sig figs. Our mass had 3 sig figs here. 100, we can assume it's 100.0 because it didn't give us that number value. So this would be 78.0, which also has 3 sig figs. So if we round our answer to 3 sig figs and put it in kilojoules, it would end up being 17.9 kilojoules. So that is the value that we're going to end up adding together at the very end. But we still have one more step to do. We have to change this gas at 100 into the gas at 105. So we're back to where the temperature is changing. So we have to go back to the Q equals MC delta T formula. Our mass is 55. C, specific heat for steam, like I said, would typically be given, but it's 1.99. And then our change in temperature, we are going up to 105 from 100. And that would just be a difference of 5. Multiplying it together, it's going to be 547.25 joules. Now, this probably should have had decimals here. That way we would know what it is. But we could safely assume that we're going to round it based off of our mass that's given here. So this would end up, whenever we change it to kilojoules and round to the 3 sig figs, would be 0.547 kilojoules. And whenever we add those together, it's going to be 142.447 kilojoules. But remember, whenever you are adding, in terms of sig figs, you round to the least number of decimal places. Our second one has a whole number that does not have a decimal place. So we would need to round this to the whole number, which would be 142 kilojoules. So be careful on sig figs with the thermo problems. They tend to be rather tricky, especially with those temperature changes. But you can generally use your mass, however many sig figs are in your mass, to do the sig figs for each individual problem. So that was looking at a heating curve where it was constantly absorbing energy as time went on. We can also look at this if it is decreasing energy and releasing energy as time goes on. So here's a cooling curve for water. Notice that it still has the same melting point and boiling point, but remember it is now going to be condensing and freezing, so going the opposite direction. With these, your temperature changes will end up being negative because the temperatures are going down. And then in terms of the phase changes, because we said this is still releasing energy, instead of vaporizing, we are now condensing. It is still going to be the exact same number value, but instead of absorbing that energy, it is going to be releasing that energy. So our delta H values, when we plug them in, will end up being negative if we are cooling. So something to remember, if we are increasing and going up, all of those Q values were positive. Our delta T values and our delta H values were negative. But if we are cooling and releasing energy, our Q values should be negative, our delta T's would be negative, and our delta H's would be negative. Looking at delta H we refer to as enthalpy, which looks at the heat content of a system at constant pressure. So we typically use enthalpy whenever we're discussing heat changes in a chemical reaction. And heat of reaction that we typically look at, that delta H, refers to our change in enthalpy, so the change in heat over the course of the reaction. In terms of enthalpy, and this should be a slight review from Chem 1, if reactions release heat, so enthalpy of the products is less than that of the reactants, so it released energy, it has less energy overall, that delta H value is negative. Q will also end up being negative in this case. And the type of reaction, if it is releasing heat, is exothermic. So remember, exo means out of, so heat is moving out of the system. If the reaction is absorbing heat, meaning the products have more energy than the reactants, delta H is positive. In this case, Q would also be positive. And these types of reactions are going to be endothermic. So remember, endo is inside. Heat is moving into the reaction. These we could have seen a little bit in our kinetics unit where we looked at the potential energy curves. So remember, with potential energy, we looked at the heat of reaction is the difference between the reactants and the products was our delta H. So in this case, the products had less energy, so it was a negative delta H value. If the products have more energy, that's when it's that positive delta H value, and it absorbs heat. Another way that we can look at the energy from a reaction is by actually looking at a thermochemical equation. So this shows the chemical equation like we've normally looked at, but it also looks at the heat of reaction in terms of that specific equation. So the given heat tends to refer to the reaction as written with the mole ratios in the reaction. So here's an example thermochemical equation. We have methane and oxygen reacting to produce carbon dioxide and water. And the delta H value here is negative, meaning it is releasing that energy. So this is releasing 890 kilojoules of heat. So in an instance like this, you might see heat as a product because it is releasing heat. So you may see it written separately, or it may be part of the equation itself. So let's look at how to actually use this in terms of a calculation. So we can do stoichiometry using this heat of reaction as written as part of our mole ratio since it's in the equation. So here it says, given the following thermochemical equation, and it's the same reaction with methane and oxygen, says calculate the amount of heat produced when 25.1 grams of methane react. So we're ultimately trying to find heat. So we're trying to find kilojoules, and it gives us grams. So we're going to start with our mass as given. So the 25.1 grams of methane. Before we can get to kilojoules, we need moles. So moles is still always our first step. So we need to get rid of grams. It will go down at the bottom to change into moles on top. Molar mass for methane is 16.042 grams. So that's going to cancel out grams. Now we have moles of methane, but we're looking for kilojoules. So we have to get rid of moles of methane. In our reaction, there's 1 mole of methane. So that goes on the bottom. And that is per negative 890 kilojoules. Oh, excuse me, I forgot the K. So that is going to allow us to cancel out moles and give us kilojoules as written. So we solve this just like normal. If you put this in the calculator, you get negative 1,392.5 kilojoules. In terms of sig figs, remember, look at your original numbers. That 25.1 had 3 sig figs. So this would end up being negative 1,390 kilojoules. Another way that you could say this is, since it wasn't no like heat produced, we could also write this as 1,390 kilojoules of heat released. Either way you see it, these are equivalent to one another, so either answer would be accepted. Most of this video was review for Chem 1. Whenever you look at the second video, it is going to be all brand new stuff of calculating heat of reaction. And a lot of it will be using values from your textbook or values that would be given based off of the type of question. But there's going to be 3 new ways that we look at calculating heats of reaction that we did not cover in Chem 1.